Hello, everyone, and welcome to our webinar on DFN Based Evaluation of Interim Scale Non-Daylighting Wedges in Open Pits. My name is Marisol Valerio. I'm a Principal Rock Mechanics Engineer at WSP, and I'll be moderating today's webinar. The webinar will present a discrete fracture network-based approach that has been developed by WSP to identify multi-bench scale rock blocks in open pit slopes and evaluate their stability using a 3D probability of failure solution. This work builds on several years of applications of the DFN 3D POF approach. The presentation today will be about 30 minutes long and will be recorded, and a link to the recording will be provided after the webinar. If you have any questions during the presentation, please submit them through the questions box of the GoToWebinar control panel. We'll have about 15 minutes at the end to go over the questions. And with that, it's now my great honor to introduce our presenter, Dr. Steve Rogers. Steve is a senior principal geoscientist and rock mechanics consultant with WSP, who has been using DFN methods for characterizing fractured rocks and reservoirs for over 30 years. And with that, I'll pass it over to you, Steve.
Thanks, Marisol, and good morning, good afternoon, good evening, wherever you are in the world. It's great to be with you today. Unfortunately, due to technological problems, there seems to be a problem. We'll not be able to show my face, so you're spared that. But let's get on with the presentation today. And please, at the end, there's after the questions, my contact details are there. So there's a lot to get through. So often, if you've got other further questions, please do drop me a line, and I'll try and help you out. Just to start, myself and Marisol both work for WSP Mining, which is a 5,000 plus team of dedicated mining staff within the WSP group, and offering a wide range of mining services. We sit within mining engineering and stability, so obviously that's very much the theme of what we'll be talking about today. And just to give you a little bit of a sort of an outline of what we'll be talking about, something about the background of why we need to be looking at what we're going to be talk about and just a little overview of DFN modeling, and also looking at how we can predict and identify wedges forming in a slope from DFN models, how we can evaluate their stability, and then how we can understand the results we get from the 3D POV analysis, and just some final conclusions. And as Marisol said, this will take maybe about 25-30 minutes, and then some time afterwards for questions. So really the assessment of the stability of structurally controlled slopes. And when we say structurally controlled slopes, we mean slopes that have either got a strong structural failure mechanism or some hybrid with rock mass and structure. It always involves incorporating, either implicitly or explicitly, some kind of structural model into our analysis. And obviously, evidence points us to the fact that the majority of failure mechanisms in these slopes are strongly influenced and controlled by these structures. And so we have this challenge of, okay, how do we incorporate them such that we can make better predictions? Well, there's a number of challenges that go with this problem. The explicit representation of faults in numeric analysis certainly comes at quite a computational cost. So that's the first thing. The more structures we put in, the slower the analysis goes. Usually it's only the major structures that are defined to a reasonable degree of accuracy, which means there's an awful lot of structure that's not incorporated, as well as the uncertainty with the structures that we have already defined. And then if we don't try to explicitly define these structures and use kind of implicit analytical solutions, they often either grossly simplify the structure or perhaps not even capable of capturing the complexity we need for the analysis. So, a key question is, how can we bring sufficient structural fidelity to analysis and also be able to address some of these issues around uncertainty? Again, thinking about these sort of structured, faulted rock masses that so many of the large open pit mines have developed in, is like, how do we capture all of the structures when there's really just too many to map. We know we have to have a cutoff of size. So that's, how do we incorporate that? This picture on the bottom really is it's actually showing in a way it's a distribution of the size of structures that we would see in the pit. So it's like the trace length of these structures in meters along the bottom and the kind of cumulative count. And we know that at the big end of the major structures, we map and we wireframe structures in the maybe hundreds of meters upwards to sort of at the pit scale. The interamp scale, these sort of around about sort of tens to hundreds of meters, we might be capturing some of those structures explicitly and be able to wireframe and know where they are. But certainly as we get smaller and smaller, we know there's lots of structures that are detected, but they might actually be unmapped, and they're certainly not wireframed. So we have this problem where, at the big scale, we know with reasonable confidence, and as it gets smaller and smaller, there's more and more structures being introduced that we're not entirely sure where they are, and we have to find some ways to incorporate that. And since we're thinking not just about structural geology, we're thinking about stability, we have to ask ourselves some questions that go along with that. So, such as, what's the probability of unknown critical structures being present in our next interamp stack? So what's the likelihood of finding something that's, unfavorable? And what's the probability of this structure and perhaps known structures collectively forming a rock block greater than some critical size? And what's the probability that this rock block might be unstable? And really that's what we're at the heart of what we're trying to address. And what we're talking about today is like trying to think about blocks, probabilities, volumes, and uncertainties around those properties. So how do we incorporate this structure that we're not quite so certain about? We see evidence for, but it's just too hard to wireframe up. And that's, we use this technique called discrete fracture network modeling. Lots of people do this. And really the idea is we're going to try to represent the relevant elements of structure, whether that's fractures, joints, faults, beddings. The components that we add are really a function of the nature of the problem we're trying to solve. Really, what we're talking about today is almost adding sort of smaller intermediate scale faults largely, but perhaps if we're actually looking at just a bench scale problem, it might actually be just joints that we're thinking about. But we're explicitly representing these structures stochastically in 3D space. Stochastically just means that the parameters are defined effectively by distributions, and so we're statistically generating these models. As it shows in the top right, these little green histograms, just to illustrate the key properties that we need to define a DFN model is the orientation properties, the size, the intensity. We can add some material properties, cohesion, friction angle, permeability, even if we need that. But the fourth property is really the spatial variation or the fracture architecture. How do those fractures or faults organize themselves within our rock mass system? We're going to transform geological and geotechnical data into these distributions, and we'll use those to actually describe the fault or fracture network. When we do that, the model itself will also incorporate the major wireframe structure. So we're not replacing those, we're just supplementing often a smaller population. And often when we do this, there's dependencies between those smaller structures and the larger structures that we'll look at briefly in a little bit. And as I said, because it's a stochastic process, we can build many equiprobable realizations, and that allows us to actually carry out some probabilistic assessments. So we can look at the likelihood of certain things happening. Okay, so an important part of the actual DFN model generation, though, is to think about how those structures are organized. Sometimes it's actually quite simple. Model on the top left, often we just see relatively simple fault patterns, but often they can be quite complicated and perhaps quite ordered, whether they're ordered in the sense that they have some strong mechanical layering, maybe there's predictable deformation patterns where actually the faults themselves are rotating around as they move from one side of the pit. Maybe they're clustered. So it's important to try to incorporate this sort of structural pattern into the DFN models. But as a little bit of a warning, it's really important to ensure that we always balance the pragmatism of a geotechnical solution with the elegance of structural modeling, erring towards better constraint to data than structural beauty. It's important to remember that geotechnical engineers and structural geologists have very different perspectives and goals. And since the stability regime is very much the purview of the engineer, it's important to keep them happy. But at the end of the day, a good DFN model is one that honors the observed structural data, but also has a sound conceptual fracture model behind it. I'm sure there'll be questions around that. So how do we actually build the model? Well, the key inputs for the data, it's just a regular sort of site investigation data that you collect in your mine, whether it's mapping from photogrammetry on the bench or cell mapping. That will give us some length scale of structures at a certain scale, as well as some orientation data. Obviously, the wireframes that we see mapped here, the mapped major structures, these are an important part of the model that we put together. This graph here shows this is a power law analysis where we've actually integrated the size distribution of major structures with smaller structures from pit mapping. In this actual case, underground mapping. This is some work from Chucky Kamata. I'll actually have the reference for the paper later, that shows actually the size of structures there could actually be described by a constant power law distribution. And that's a very common technique we use for defining the size of structures. Borehole logs, again, give us intensity measurements and orientation data that we could also get from the mapping or logs. So these are the range of data that we're just going to use to derive the inputs for the model. In terms of actually building, we're going to talk really about pit scale or sort of slope scale DFN models today, although they can be built very simplistically in simple volumes. We typically use what we call a geocellular approach, where perhaps we might have a range of different geodomains, as illustrated by this grid in the background, the different color, where the model itself will have the properties of the structures within each domain defined by some kind of underlying model or properties that are defined specific to that geodomain. So it might be the intensity of structures, it might be the orientation of structures, but that way we can actually build a structural model that meaningfully matches the observed properties while also reflecting some underlying structural property. So then top right here, this is an example of, so you can actually see the large major wireframe structures, and then these are stochastic faults that are being developed around the fault. And you can see there's a number of different sets, like reds and blues, so defined by the orientations here. And then we can look, this is like an example of that same DFN, but looked at from inside the pit. So you can see, certain structures being mapped. So some of these are deterministic, and the smaller structures are the stochastic fabric that we can take to analysis. And so that's a very quick overview of how we actually put together a DFN model to actually generate these structures. I've just put those last comments. It's really important to validate our simulated model against observation. So where we've got mapping, we want to make sure that if we were to simulate a bench mapping program, it would produce the same results. If we drill boreholes into it, it would produce the same intensity. Just very quickly, I promised I'd talk about structural dependency. When we build these stochastic models, we often want to make sure that there's the appropriate relationship between the smaller structures and the larger structures. This is an example from Chucky Kamata. I just mentioned there's the reference in the bottom right, where we actually found there was a strong relationship between the intensity of logged faults and the distance to the major wireframe structures that could be seen in the pit. So it's quite a noisy relationship when you just plot all the points. However, when you average it over distance windows, we can actually see there's actually this very strong sort of exponential decline. And so in this example here, the blue data is the simulated intensity of structures, and the red is the observed intensity of structures in the borehole. So the resulting DFN here with the black faults are deterministic features, and the blue represents one realization of a stochastic model where we've accurately preserved that relationship. Okay, but let's talk more about the wedges. So once we've got the DFN model itself, we can now search to look for the formation of blocks. Now, when we do that, this is just a small example here. It's like a sort of interramp scale, 230 meters. We kind of get, there's four principal kinds of blocks. What we call there's simple kinematically um, movable but stable wedges. They're not going anywhere. Small wedges, same. We can have unstable ones like here. So it's just like a little wedge that would drop out of a bench. But then really what we're more interested in is what we call these large, effectively non-daylighting wedges that are, here, this example is 6 benches. This example up here is about 10 benches high. So they're stable because they're locked in. They kinematically can't actually move. There is the fourth case that's not actually shown here is obviously multi-bench kinematically unstable wedges. So if it's maybe just formed by 2 faults, and we often see this when we actually pursue it as we go down the pit, we repeatedly are having wedges dropping out of that long narrow wedge. But really we're more interested in these identifying these large potentially unstable wedges. They're locked in, but we have to ask how locked in, how stable they are. Now let's just look in a little bit more detail at one of these non-daylighting wedges. This is this sort of slipper in a way. It looks like it wants to come out. It's about 140 meters long. It's 1, 2, 3, 4, 5 benches long. If we look from the side though, we can actually see. So it's a wedge, but it's sitting behind this buttress of rock mass. That's actually what's calculated, well, what's keeping it stable. So one of the problems is in this situation, conventional kinematics doesn't work. It just effectively says, look, it's locked in, it's got a factor of safety of a default number like 100, but that's not really the case. So we need a solution to actually be able to identify, considering both the kinematics and the rock mass component, what is the stability of this wedge. It is important just to point out the formation of this wedge is from a combination of these these are actually major faults defined, they're actually mapped, but it's also the stochastic fabric as well that helps form this wedge. So it's not just as simple as just saying it's a fault. It's always, or it's a big fault. And that's part of the question we're trying to think about. It's like, how do we think about the likelihood, given there's also some other things that we can't see. Anyway, in terms of the evaluation of stability, then we use the 3D POV code that we connect through to our FRACMAN analysis. Uses a custom slip solution. There's the reference here. That effectively evaluates the stability of this rock mass buttress. So it takes the whole volume, considering this buttress, and calculates the stability, considering both discontinuity strengths and the rock mass components. So here on the right, you actually see there's a rock mass component that really we have to evaluate as well, that's sitting in front of this non-daylighting wedge. In terms of the calculation of those strengths, the properties that we put in are rock mass strength, so kind of hook round properties, density, UCS, GSI, MID, and discontinuity strengths for the actual joints, so just cohesion and friction angle. But when we calculate the stability, the actual factor of safety of these wedges, rather than just doing it for base case strengths, we actually run a whole range of different sensitivities because it's computationally very cheap to evaluate those, just taking milliseconds effectively to recalculate, given perhaps a range of different pore pressure cases. We could do cohesionless strengths, lower friction angles, so we can run a whole range of sensitivities to identify some critical controls up front, just while we're running the analysis. So just this graph here, we can just see how for this particular wedge, as the pore pressure increases, this is displayed as a function of RU, which goes from 0 to about 0.4, so 0.4 being approximately hydrostatic conditions. You can see the factor of safety falling. So that's one wedge. So how do we evaluate a whole slope or or multiple wedges. So the kind of workflow is this. So we build a DFN model in FRAPman, and then we identify blocks. Now, there's only one block shown here, but obviously you remember that small image we started from where there was actually multiple blocks. We take those blocks into 3D POV, where it will then calculate the factor of safety of all of those blocks, considering rock mass, joint, and pore pressure conditions, knowing where it is in the slope. So it knows these are different domains. So, and then we'll run this, you know, a large number of times. Typically, we run about 100 realizations, which will generate somewhere in the tens to hundreds of thousands of blocks. And then how we post-process these results is we have a table of results, and we just and then process the blocks to go, okay, what's the probability of failure for each domain, what's the likely failure tonnage, and some other ways. We'll just look at some of the other ways we can display these results. So on the left here, this is the actual initial block formation results we get from FRAPman, and when we pass those into 3D POV, it now calculates the factor of safety. So for each of these blocks has now got a true factor of safety. So you can see these kind of ready blocks here. These are all with a factor of safety of less than 1. But obviously, that's just one realization. So we need to think, how do we compile the results for a large number of cases? Well, we use these what we call block formation risk maps or heat maps. So these represent the compilation of 100 different realizations. We take all of the blocks. So now we're seeing where are the unstable blocks forming all of the time in those 100 realizations. So where this graph on the left is called block failure percent, which represents the number of cases where the blocks are failing out of 100. And you can just see how the high heat colors correspond to these red historic failures. This is actually from Bingham Canyon. The reference I think was on the previous slide. So block failure percent is really a little proxy for probability of failure. The picture on the right is what we call block probability of occurrence, and really is saying where are blocks wanting to form. So that's, it's the agreement though in terms of the match between, the block failure percent and the historic failures was really quite stunning for that, and it would encourage you to read about that in a reference we'll send you afterwards. Again, remember we ran all these different sensitivities, so these actual heat maps we can actually very quickly compile what will these heat maps look like for different, say, pore pressure conditions. So this is going from dry, a little bit of water pressure, and obviously at hydrostatic conditions you see large portions of the slope are experiencing very high failure percentages. So that's it's a really useful tool just to be able to say, well, what if actually we're not so confident with our GSI properties or intact strengths. Obviously, it's we said right at the beginning it's a probability of failure method. So really, what we can do is we can actually look for each domain. We can say what is the probability of failure of this analysis. We're defining probability of failure as the volume of unstable blocks divided by the volume of all blocks. And obviously, it can be spatially mapped. But here, let's just look at a histogram. What we've got is we've got some analysis that had 7 different domains, and they're plotted with increasing pore pressure conditions. So RU, so again, dry, RU of 0 up to an RU of 0.2. And we typically put on the probability of failure 10% and 5% lines as from the Reed and Stacey guidelines. So you can clearly see that as pore pressure increases, the probability of failure is rapidly increasing to unacceptable levels. And it certainly shows the importance of pore pressure on stability, and shows how some domains often are very, very sensitive to those pore pressure increases, where perhaps others aren't, where they're a lot stronger. Okay, in terms of predicted failure tonnage, well, obviously that's part of the analysis anyway, because the probability of failure is the failed volume over the total volume. So we've got that failed volume, which calculated for a domain, but it'll also be mapped. So what we've got here is, if we think about this as This is our block failure percent kind of heat volume. We're looking a little bit deeper into the slope, so that actually gives us a way to calculate the failed mass is effectively the mass of one cell, is like mapped into a grid, times the sum of all of the block failure percentages for the in a particular area of interest. So what that gives us is a way to calculate the cumulative failed volume, say, per elevation, per bench number, or any other variable that we can actually flag into a grid. So what we've effectively got here is a graph of cumulative failed tonnage predicted with elevation for a particular part of the slope, which again is it's a useful tool in terms of sort of operational support and to help the actual engineers actually kind of manage the future slope in terms of its need for mitigations and remediations. Okay, using a very similar approach to just the probability of failure. Obviously, we could run one analysis 100 times, and that gives us a probability of failure. But what we can also do is we can repeat this analysis for a range of different interramp angles and slope orientations, and then that actually gives us a design chart showing probability of failure as a function of increasing interramp or even small rotations on the slope. So we can just see here the blue, this represents the actual main design azimuth with its probability of failure rising as we increase the interramp. But comparing that to a design rotation of 10 degrees counterclockwise or clockwise. So it's a very useful tool in terms of both the design uh, looking forwards in terms of design and prediction, but also in terms of understanding past failures. So if I can just wrap up, it's been a pretty rapid 30 minutes. I do appreciate your time. So I think what we've really found is that DFN modeling provides a very efficient way to model the intermediate scale structure that we can add to the known structures. So it allows us to capture some of the uncertainty associated with the structural model. We've got ranges of properties that we can test easily, and it allows multiple realizations rather than just one. That's one of the dangers of explicit modeling, is the fact that you just have one structural model, and maybe we don't have all of the structures, or the structures themselves aren't quite in the right place. So this stochastic approach to build multiple realizations is very powerful. The DFN model allows us to identify the blocks forming on the slope. So that gives us a likelihood. We say, okay, in this particular slope, what is the probability of a wedge of a certain size forming? And that's very, very useful, very critical. And in the majority of cases, certainly our experience has shown us that it's the combination of both the major map deterministic structures and the stochastic structures that want to form these larger kind of non-daylighting wedges or blocks within the slope. The 3D pod analysis just gives that extra kinematics plus analysis that allows us to identify the stability of those wedges, considering both structure and rock mass in a truly probabilistic way. And because of that, the ability to process the sensitivities at the time of calculation, it really gives us a fast and robust way to identify what are the critical controls on the stability of that part of the slope. We've used this technique now successfully over a number of years, as I said at the beginning, actually, for both predictive design purposes, but also back analysis of failure. So it's a very, very powerful tool just for understanding these sort of structured and hybrid rock mass structure failure mechanisms. And I really feel it's going to be a very powerful and useful tool over the years to come. So thanks very much, Marisol. If I can just again remind you, we come from the sort of open pit business in the mine stability part of WSP. So we do offer a wide range of services to your open pits, and we'd love to talk to you about those at some point. So thanks for your time, and I'll hand you back to Marisol for any questions.
Thank you, Steve, for the wonderful presentation. We will now be moving on to the questions portion of the webinar. So if anyone has any additional questions as we're going over the ones that have already been submitted, please continue to enter them into the questions box of the GoToWebinar control panel. So we have about 10 minutes for questions here, so we might not be able to get through all of them. The first one I have here, Steve, is does the DFN 3D-POF approach for pit slope design require different or additional data compared to other methods?
I don't believe it does, actually. It really it's built on mapping data, on logging data, and lab testing data. So it can be used on any pit. As I said, really its main aim would be looking at where you've got this the ideal case would be, strong structural component and a rock mass that's perhaps, medium to strong. Obviously, if the rock mass is very weak, it becomes not the right tool for that problem. But yeah, anyone could do it.
Thanks, Stephen. Somewhat related to the question of inputs, there's a couple of questions here on persistence of discontinuities and related to mapping. So I'll combine this into just the one question. Do you have any recommendations for assessing the true continuity or persistence of discontinuities? And is it possible to integrate mapping data from, for example, photogrammetry or LiDAR into the DFN models?
Great. That's great questions, Maricel. Thanks. So yes, you can. We use photogrammetry and LiDAR and all sorts of, photogrammetric techniques all the time. One of the things we do find is, though, that the size range of the structures that we're looking at within the scale of the pit is generally bigger than what has been mapped at the bench or one or two benches, which is often where the scale of the photogrammetry is. And so that's why I mentioned the power law analysis, where really we're trying to find ways to combine those observations that in the tens of meters, along with structures that we can already see that are maybe hundreds to even potentially kilometer scale, because evidence shows us that that the power law distribution of sizes is perhaps the most common, or one of the most common descriptions of size. And so we have to find these ways to be able to use these smaller scale mapping techniques and combine it with the observations that we see at the larger scale as well. I hope that addresses those questions.
Thanks, Steve. Now, switching gears a little bit here, what are some of the main advantages of the DFN 3D-POF approach compared to other similar tools, for example, rock slope and other similar ones?
Yeah, thanks. Okay, so I mean, I've played a little bit with rock slopes, so I can see. I think one of the big differences is that the Fracman 3D POF solution allows the computation of a large number of blocks a large number of times. So the power of the DFN produced in Fracman to be able to run a whole pit slope 100 times or even more is just the biggest difference. The rock slope is, it's got a great algorithm for finding blocks, primarily with I think deterministic structures, but it has some DFN capability, and that's great. But I think it's the fact that we can be analyzing hundreds of thousands of blocks to get a really robust assessment of stability and the probability of failure on a particular part of the slope I would say would be the key difference.
Thanks, Steve. A few questions here regarding inputs and how they affect the calculations. Does RU affect the pore pressure both in the rock mass and in the joints?
Do you know, that's a very good question that at this moment I believe it does, because it should be an effective stress calculation. I believe it does. I would have to confirm that though.
Thanks, Stephen. Related to that, there's a question here around flow. Can DFN models help to determine if fractures act as flow conductors or flow barriers?
That's an interesting question. Sort of. The DFN model itself, I don't know if it necessarily answers that particular question, but it is a very important question because at the scale of, at the operational scale of a slope, let's say the interramp or even smaller, clearly the flow of groundwater is through a relatively limited number of key conductors. And so DFN models actually provide a really good way to describe why it is that when we drill some drains, only maybe 70% of the drains actually produce flow, or only a small number actually seem to effectively depressurize the slope. So I'm not sure it completely they on its own would answer that question. That would take some other thought and analysis, or potentially modeling, which of course DFN would. But certainly in terms of, can DFN models handle that flow component of the slope problem? Absolutely, yes.
Perfect. Thanks, Steve. Now, just conscious of time here, we might have enough time for a couple of questions. What simulation techniques do you use for the DFN model? Is it geostatistical simulation or spatial Monte Carlo type simulation?
I think it would be more spatial Monte Carlo type simulation, but imagine you had a lot of data. There's no reason why you couldn't actually have used geostatistical modeling to produce a good quality description of intensity, say, and how it varied through in a part of the slope. So then when you make your Monte Carlo models, the actual, say, intensity of faults would be being controlled by the underlying geostatistical intensity property. So I think we use a little bit of both, but in terms of the modeling itself, that's very much a sort of a Monte Carlo approach.
Thanks, Eva. Then going back to formulating input parameters, there's another follow-up question here on generating inputs for discontinuities. Can you incorporate televiewer and logging data into the analysis, or is it only mapping data that's used?
No, actually, in terms of how we define intensity, we actually define intensity primarily from borehole data, either geotechnical logging or televiewer data. So that's our primary input. In terms of the orientation components, I prefer mapping because mapping is a bit less biased than obviously borehole data. But again, it depends. If you have a good spread of orientation data within a particular domain, and you can generate, a robust, appropriately weighted SteriNet, you could do things entirely from borehole data. Yeah. So I'm sorry if I implied that mapping is king. Mapping is not king. Mapping is a good component, but also, borehole data is very important as well.
Perfect. I think we're getting close to the end here, so we're 5 minutes remaining. I think we'll have time for just the one additional question. And again, if there are questions we didn't get to, we'll be getting back to everyone after. So, Steve, the last question I have here is, can this kind of methodology be applied beyond open pit slope problems, such as stability assessments for railways and road cuts?
Well, a great question. Here in British Columbia, where we have about a good 5 mountain belts to that all our linear infrastructure of roads and railways and pipelines all have to find their way through. Obviously, there's lots of natural stability hazards, and it's very much the same inputs. We're thinking about a rock mass that's got a lot of structure. The rock mass is not always very strong, so sometimes that rock mass itself is going to be represent a key input to the stability of a bit of a slope. And so there's absolutely no reason why DFN model couldn't be combined with campaigns of discontinuity mapping through photogrammetry and drones to produce stochastic representations of slopes above railways and roads and pipelines where possible. I think there's absolutely no issue at all about that.
All right. Well, with that, that concludes our webinar for today. Thanks again, everyone, for joining us. Link to the presentation recording will be provided after the webinar. And again, if you have any other questions or you'd like to learn more about how these DFN methods could be used at your site or at your project, please reach out to Steve or myself. We'd be very happy to hear from you. Thanks again, and hope you have a lovely rest of your day.